Hello everyone, today we'll be discussing the chain rule, and there's actually two cases, one where our functions x and y are functions of one variable, and the second case would be when x and y are actually functions of two variables each. But we'll get to that soon enough. For right now, let's just kind of focus on the first case where x and y are functions of only one variable. And let us actually recall the big result from the last video, which is that the total differential dz is equal to the partial of z with respect to x multiplied by dx plus the partial of z with respect to y multiplied by dy. So with this in mind, notice if you divide this equation through by dt, you actually get this result, which is a nice way of showing that, but in reality, to prove it, you need to be a little more rigorous and detailed. Basically, you divide by delta t, and then letting delta t go to 0, we end up getting these derivatives, which is kind of nice, but long story short, just look at this, divide by dt, this is true. Okay, now let's read through. So chain rule here, case 1 says, supposes z is equal to f of x comma y, function of two variables, that's differentiable, where x and y are each their own function of t. Let's call the one for xg and the one for y h. Notice f is already taken. And they're also differentiable, let's say. Then then z actually is also differentiable as a result. And moreover, this equation ends up being true. That dz dt is equal to the partial of z with respect to x multiplied by dx dt, so derivative of x with respect to t now, and partial of z with respect to y multiplied by the derivative of y with respect to t. So really this is just the chain rule, only now we have these two pieces which end up being a part of what came from this total differential equation. So I'm going to erase this now. So now what we're going to do is we're going to do this in one example. And I honestly think this is really all we need for this case, so let's take a look. So we're asked to find dz dt when t is 0 for this function z of x and y, where x is sine of t and y is cosine of t. Right, so let's see what we can do. Let's see what damage we can do right away. So dz dt, using this equation I boxed in red, is what? Well, it must be the partial with respect to x, which notice derivative of x squared is 2x, y is a constant, so multiplies down for free, plus derivative of this with respect to x, the x drops, so we get 3y to the 4th, multiplied by dx dt. Look at this. So if x is sine and y is cosine, then right away we can get x's derivative dx dt and y's derivative dy dt to be what? Well, derivative of sine is cosine of t. Derivative of cosine is then negative sine of t. Perfect. So that means dx dt really is just cosine of t, which is nice. Plus dz dt, well, partial z with respect to y, I should say. So derivative with respect to y now, letting x be the constant, the y drops, so we just get x squared for the first term. Good. Derivative of y to the 4th, notice is 4y to the 3rd. 4 times 3 is 12, so we get plus 12. X, y to the 3rd. X comes down for free because remember it's a constant when taking the partial with respect to y. Multiplied by dy dt, which is negative sine. So what I'll do, if you don't mind, I'll just attach the sign and change the sign to negative. Okay. And now look at this. We want to find this derivative when t is 0. Now notice, when t is 0, x is sine of 0. So this implies that x is actually equal to 0, because sine of 0 is 0, notice. And y would be cosine of 0, which is actually 1. So all of our x's become 0s, and all of our y's become 1s. 1, not 0, sorry. Okay, so let's see what we get. So we end up getting is that dz dt is equal to, so let's see, I think we can do this. So we get 2xy, so that's going to be 0, plus 3 times 1 to the 4th, such as 3. Cosine of 0 is going to be 1, minus, this is going to be 0 squared, so it's 0, plus 12 times 0, so that 0 is out. And in fact, since sine of 0 is 0, that just, this whole thing becomes 0. So that's kind of nice. And in reality, all we really have left is 3. So the answer here is just 3. Now, something that I must say is you can always verify this yourself by doing it the long way. What do I mean by the long way? Well, actually plug it in. We'll plug these in. So if you let x be sine of t and y be cosine of t, you can actually expand things out. I don't think anything really combines, but you can certainly actually plug them in and get this kind of nasty sum of products of sine and cosines. And then take the derivatives of that, or the derivative of that function, because now it's only with respect to t now, one variable t. The only issue is that that involves quite a bit. I mean, that'll involve all sorts of things. It'll involve chain rule and product rule, and the result will be really, really large. But then afterwards, once you've gone through taking the derivative of that crazy thing after plugging things in, setting t equal to 0, you should get 3 as well. So it's a nice thing to verify, but on your own, I'm not going to do it. But what I will do now, though, of course, I'll go over case 2 for the chain rule. We'll start to see a very similar idea, only where x and y are each functions of 2 variables now. So let's see how that plays out. Okay, so now here for case 2, we say that, again, very similar setup, only here for our function f of x comma y, x is a function g of 2 variables s and t, and y is a function h of 2 variables s and t as well. And also these are differentiable. So then the following is true. Notice I'm not saying that z is differentiable necessarily because we're taking partial derivatives and we're not taking the actual one derivative. And the reason why that's true is because if you think about it, if z is a function of 2 variables, but they're each in terms of 2 variables, then z is still in terms of 2 variables. It's going to be in terms of s and t. With case 1, if we were to plug x and y into this function, then really z is only a function of 1 variable, t, if that makes sense. So with that being said, you can legitimately take the derivative dz dt. But in this scenario, since x and y are each function of 2 variables s and t, then in reality, z is a function of those variables s and t. So in fact, very often z is called the dependent variable, where s and t are independent variables, and x and y are the so-called intermediate variables. So just kind of bear that in mind. And what we end up getting are these two similar facts to what we saw previously, but now, of course, it splits into 2, one for s and one for t now, one for each variable. And notice everything is partial here. Unlike with the previous case, we actually had straight up d and no partial symbol. Well, we have some partial symbols, but here everything's partial as it turns out. So I'll just read it out. Partial z over partial d is partial z partial x times partial x partial s. And the reason, again, why we need partials everywhere is because everything in sight is a variable of 2, well, a function of 2 variables. There is something that people tend to remember sometimes. I think is pretty useful. If we have this kind of tree showing that what function is dependent on which variables, notice x or z is dependent on x and y, but they're intermediate in the sense that x and y are each dependent on s and t. So if you wanted to take derivatives upon each of these branches, then basically what you would do, if you wanted to take the partial with respect to, let's say, s, then you need to land on s with each partial branch, and then add those results. So this line here would be partial z over partial y, and this line here would be partial y partial s. This graph, or this branch, will be partial z partial x, and this x to s will be partial x partial s. And what you do is you multiply with each branch, and then add those product results together, and you end up getting partial z partial s if you land both on s. If you do the same thing but land both on t, then you get a diagram explaining the formula here. So this is just a nice way to remember which what. But honestly, the way I do it is I just imagine that the x's cancel, you get dz ds, the y's cancel, you get dz ds. But there's 2 of them because you have 2 variables, and that's true because of the total differential, basically. So now, cutting to the chase with this example, let's see if we can utilize these. So here z is equal to this function e to the x times sine of y, where x is st squared and y is s squared t. Oof, so that's going to be a little bit to think of. But you know what? Here's what I'm going to do. I'm just going to lay all our cards out for a moment. Let's look at partial z partial x. So partial z partial x is derivative of x of e to the x is itself. Sine of y is a constant, so that's it. Similarly, partial z partial y now, well, now e to the x is a constant, and derivative of sine of y is cosine of y, so we get e to the x cosine of y. Perfect. Now, on the other hand, we need the partials of x with respect to s and t, and y with respect to s and t. So let's see. Partial x with respect to s is dropping the s, so we get t squared. Let me write a comma here for the next partial. So partial x with respect to t now would be bringing the 2 down with the power rule. So that's 2st like that, if that makes sense. Derivative of t squared is 2s, or 2t, and the s multiplies for free. And for partial y with respect to s and t respectively, let's see. Partial y with respect to s is, let's see, so we have the power rule here. So that's 2st, and then partial y partial t now. The t drops, so that just becomes s squared. So they're super similar looking. And how can we find partial z, partial s? That's one of the ones we want to find. Well, according to this, we need to multiply partial z partial x with partial x partial s, and add that to partial y, z partial y, multiply with partial y partial z. Which sounds like a bit of a nightmare, but it's just really selecting which ones to multiply. So it's a partial x partial z multiplied by partial x partial z. So let me write it like this: t squared e to the x sine of y plus partial z partial y multiplied by partial y partial s. So that's 2st e to the x cosine of y. Hope I have enough space here. Kind of squeezed in. Let me just move the camera. Whoa. Sorry for the shake there. I guess we could pull stuff out if you want. Like if you wanted to pull out what they have in common. They have a t e to the x in common. What you end up getting is t sine of y plus 2s cosine of y. So that's kind of nice to see that maybe, but it's not really too important. But I will box this one. It looks a little nicer. But now partial z partial t now. So partial derivative of z with respect to t now is going to be what? Well, again, we still need these, but now instead of multiplying them by the s's, we're going to multiply with the partials with respect to t. So it's going to be this times 2st. So it's 2st e to the x sine of y plus this guy again, but now multiplied by s squared. So let me write the s squared in front. And that's going to be, again, e to the x times cosine of y. And just because I don't have too much space, I'll do it anyways, it's fine. So let's pull out s e to the x in this case. And we have 2t sine of y left over on the inside plus 1s and a cosine of y left on the inside right here. So I hope that makes it onto the screen. So that looks kind of nice. All right, so yeah, it's a little bit of work, but honestly, it's just kind of using these facts here to make sure that it helps us in getting our products right. Now, the next thing we would need to talk about really would be doing this with more variables, which sounds like a little bit of a pain. I think we'll just see one example where they're going to be each of 3 variables, but we're going to have to see it. So let's get to it and let's see what happens. Okay, so like I said, we're going to try to take things just a little bit to the next level here. So notice here we have this function u of 3 variables x, y, and z, where each x, y, and z are in terms of 3 variables themselves, r, s, and t. So here what we can do is we can use this diagram, u, in terms of these 3 variables x, y, and z, and then each of these x, y, and z's are now in terms of 3 variables each, are s and t now. So if you want to follow this branch, or this branch diagram, I guess you can say a tree diagram, to actually figure out what the partial we're looking for would be, then let's do that. So we want partial u, partial s. So we need each of these. So we need partial u, partial x, and we need partial u, partial y, and also partial u, partial z. So we definitely need these. And then along with each of those, we need the partials of x, y, and z, but now with respect to s only, because we're looking for what? We're looking for the partial u with respect to s now. So let's take a look here. The derivative of u with respect to x, y, and z will just be these guys. Derivative with respect to x is going to be 4x cubed. The y drops down for free. This with respect to x is 0 because there's no x's. With respect to y, the y drops, so we get x to the 4th. And here we use power rule. Here we get 2y times z to the 3rd. Perfect. With respect to z, the first term is 0 because it's constant. And here, by power rule of z cubed, we get 3z squared with the y squared in front like that. Perfect. So now we need to multiply each of them respectively by, the partial x with s, the partial y with s, and the partial z with s. So notice I'm lining them up to partner off with what we're going to multiply them. Remember, the way I like to see it is that the partial z's, partial y's, and partial x's, quote unquote, cancel. To give partial u, partial s, there's 3 parts of it. because u is in terms of 3 variables after all. So now let's see if we can find these. The derivative of x with respect to s, the s just drops, so we get re to the t. Derivative of y with respect to s, derivative of s squared is 2s, so we get 2rs e to the negative t. Derivative of, let's see, z with respect to s, well, the s drops because it's just 1s, the power of s is 1. So we end up getting r squared sine of t. Let me just make sure we're lined up. Okay, cool. So now what we need to do is multiply each of these together and we're set. So partial u, partial s now is going to be this madness. I'm going to try to write this in a nice way. So we get re to the t times 4, well, I guess that's fine, times 4x cubed y plus this quantity x to the 4th plus 2yz to the 3rd times 2rs e to the negative t. Okay, it looks good. Plus this guy, 3y squared z squared times r squared sine of t. And now we want to see what this is equal to when r is 2, s is 1, and t is 0. Now, when t is 0, oh, look at that. When t is 0, that kind of gets knocked up to 0 because sine of t is 0. So right away, this is 0. And in fact, notice, when t is 0, that means z is also 0. So this actually, believe it or not, implies that z is 0 because z is equal to sine of t. So everywhere I see a z, I can just make that go to 0, which is really just there, actually. But that's fine. But now, what is x and what is y? Well, let's see. When so I guess we could write the results over here. So we found out that z is 0 when r is 2, s is 1, and t is 0. So that's z is 0. But now the question is, what is x equal to and what is y equal to when r, s, and t are these values? Well, t being 0 means e to the t is ignored because e to the 0 is just 1. R times s is going to be 2. R times s squared is also 2. So x and y are each 2 in this case, which is nice. And we end up getting here is r, which is 2, times e to the 0, which is 1, times 4. X is 2, so it's 2 cubed, times y, which is 2. Geez, it's kind of crazy. Plus x to the 4th, so that's 2 to the 4th, which is 16, times 2 times r, which is 2, times s, which is 1, times e to the 0, which is 1. Oof, okay, well, that's not that bad, actually. So let's multiply everything together here. So actually, if you think about it, these are just all powers of 2. So if you just count the powers of 2, this is 2 to the 1, 2 to the 1, 2 to the 3. Really, 4 is 2 to the 2. So if you add the powers here, 1 plus 2 is 3, plus 3 is 6, and plus 1 is 7. So really, we get 2 to the 7th for the first guy, and then here this is 2 to the 1, 2 to the 1, 2 to the 4th, so that's 2 to the 6th for the second one. And just because I'm a weirdo and I remember powers of 2, I know 2 to the 6th is 64, making 2 to the 7th double that, which is 128. So we end up getting 128 plus 64, which ends up being 192 in total. Awesome. Let me move the camera a bit just so you can see that, but I think it's squeezed in there okay. Nice. So yeah, this was definitely quite a problem. There's not really too much more to discuss in this section without getting kind of crazy. So let's get crazy. Let's take a look at an example now where we'll be asked to show a certain equation holds. Okay, so this problem sounds a little crazy, but it's actually not too bad once you kind of realize something. So here we're given this function g of s comma t, where it's actually equal to another function f of s squared minus t squared equal to t squared minus s squared, which sounds bizarre. And f is differentiable, so we can take derivatives of f and thus of g. Then we want to show that g actually satisfies this partial differential equation. What we're going to do actually, which may not be super obvious at first, but we want to get x and y into the mix somehow. Normally, since we have f of xy, then it's natural to do something like this. Well, maybe not super natural right away, but we can kind of see that it does make sense once I show you these. So hopefully once you see it, you can unsee that. So now, really what we can say is that g of s comma t is equal to f of x comma y, where x is equal to s squared minus t squared, and y is equal to t squared minus s squared, which I'm going to notice is equal to negative x. I feel kind of weird writing that though. I don't know how useful that'll be. But anyways, let's find out partial g partial s then. So partial g partial s is really equal to partial f partial s. And partial f partial s is equal to, well, that's going to be partial f partial x multiplied by partial x partial s plus the same thing but for y. So partial f partial y times partial y partial s. Okay, I hope that part makes sense. But now figuring out what each of these are is a little crazy. It's not too bad, but let's see. Partial f partial x. So the problem is we don't know what that is because we don't have an explicit form for the derivative of f with respect to x. But we do for x. We know x is s squared minus t squared. So at least we know this guy. So what? Let's just see. What is this guy? What is let's write it like this, I guess. So derivative of x with respect to s is going to be s squared. So it's going to be s squared. Oh, sorry, 2s times partial f partial s x. There we go. It's a little weird, but that's fine. Derivative of y with respect to s is going to be negative 2s. So it's minus 2s times partial f partial y. So we know that much is true. Does this really tell us anything? Maybe not actually right away. But what we want to do now is notice we want to multiply it by t. So maybe that'll come into play. You know what, let's just do this. Let's just find, my gut instinct is just telling me to find the other one. So we found partial g partial s, let's find partial g partial t. And of course, f is basically equal to g, so this is partial f partial t, which is equal to partial f partial x times partial x partial t, plus the other one, partial f partial y times partial y partial t. I feel like I'm talking to the board at this point. There's so much going on, but that's okay. Now partial x partial t, derivative of this with respect to t is negative 2t. So we end up getting negative 2t times partial f partial x. And then here for this guy, partial y partial t is positive 2t. So this ends up being positive 2t times partial f partial y. So look at this. It looks like they kind of cancel out, but not quite. But if we were to multiply each of them by the opposite variable, this by t and that by s, then they would indeed cancel out. In fact, I think we can show that. That t times the partial g of partial s, just a lot to write, plus s times partial g of partial t is equal to t times that, which I'll just distribute right away. So it's 2st partial f partial x minus 2st partial f partial y. So I think you kind of get the idea at this point. And then add it to this guy, which is negative 2t, but we're multiplying that guy by s, so distributing s into this gives us negative 2st times partial f partial x, plus that times s is 2st times partial f partial y. And let's see if we indeed get 0. That's what we're hoping for. So let me write a question mark here for right now. Okay, so let's see. Sorry if I'm kind of huffing and puffing too much, but let's see. For this one, these cancel out, good. And these ones indeed also cancel out. So we indeed do get 0 actually. So we have shown that indeed g satisfies this. Wow. So I think that was a pretty good example. There's still a little more to discuss though, so now let's take a look at something a little different, and then finally that'll be the end for this video. Okay, so it's a little interesting. Here we're going to be kind of looking back at what we saw in Calculus 1 as far as implicit differentiation goes, but now using the tools that we know as far as functions and multiple variables. So let's let y be a function of one single variable x, and let's suppose we have this large function of two variables, so let's consider that capital F of xy equals 0. So basically it's some expression of x and y where 0 is on one side and everything else is on the opposite side, of course. But just keep in mind that y is a function of x itself. So what we're going to do is we're going to actually try to attempt to extract dy dx by means of implicit differentiation, basically. Where f and f, lowercase f and capital F, are differentiable functions, then the following holds. And notice that this really is just a specific application of taking the derivative of each side. Notice that the derivative of this with respect to x, so df dx, if you want to think of it like this, df dx, kind of like what we saw for df dt or dz dt, so this should be dx. We're just really looking at the total differential df and then dividing everything by dx basically. And we end up getting this. Now it's really nice, notice that of course this is equal to 0 because since this is 0, its derivative is 0 as well. So really what we're looking at is this guy here. And what's really nice about this is notice dx over dx is just 1. So in fact you can solve for dy dx by subtracting that to the other side. So minus partial f partial x over, so let me write this negative out in front actually. So subtract this to that side, then divided by partial f partial y. So it's negative this fraction of the partial of f with x and with y, which is kind of nice. And if you use this kind of subscript notation that we've seen before, this is just capital F sub x over capital F sub y. So notice the symmetry of this shortcut notation here. Now this is really kind of the benefit of our new tools using functions of two variables now. So now I want to find y prime in this equation. Now remember, with calculus 1, there is a way to do it. It will involve product rule. It's a little bit of a mess, but it's not too bad. Something you can figure out on your own and verify it indeed works. But instead what I'm going to do is I'm going to move everything to one side so the zero's on the other. So this is x cubed plus y cubed minus 6xy now equals 0. And the non-zero side is going to be our, what I call the large function, capital F of x, or capital F of x comma y really. So now it's up to us to find capital F sub x and capital F sub y now. And then just using this result above, we're good. So let's see. F sub x, derivative of this with respect to x, 3x squared. Derivative of the second term is 0. Derivative of negative 6xy with respect to x drops the x and just leaves us with negative 6y. Good. Derivative of capital F with respect to y now, x cubed goes to 0. Y cubed goes to 3y squared, and then negative 6xy will go to negative 6x because here the y drops. And with this in mind, and with this in mind, we end up getting that dy dx is nothing but negative fx divided by fy. And in this case, notice you can actually divide top and bottom by 3. And if you want to distribute the negative into the top by swapping these two at the same time, we get 2y minus x squared. The denominator is y squared minus 2x. So notice I just swapped the difference on top. I distributed the negative in, and then divide each coefficient by 3. Awesome. So I think that's all I want to say as far as that one goes. That was kind of nice. It's a quick way of finding the derivative dy dx, again using what we've developed with functions of two variables. So now we're going to take this a little bit further and actually find now a similar scenario but for partial derivatives with a function of three variables now. So if z is f of x comma y, it's going to be analogous to this. So let's take a look at that finally, and that'll be the end for the video. Okay, so this should look very similar to the previous screen we had. And here we have z is equal to a function f of x comma y. And suppose that capital F of x comma y comma z is equal to 0, where capital and lowercase f are differentiable functions, then this holds. And this is, again, essentially true because the total differential of f with respect to x in this case, well, really it's the partial f with respect to x. And in fact, what we can do is we can take the partial of f with respect to y and get a very similar scenario, only these, let me underline them in red, I guess. These dx's would, or partial x's, would now be partial y's in the partial y scenario, but I didn't want to write too much, so I just wrote the x version. Now what's really nice, notice, is that partial x over partial x is just 1. Partial y over partial x is actually 0. Now why is that the case? Because, well, partial over partial x, so the partial derivative with respect to x of y is equal to 0 because y is a constant in the eyes of x. Okay, so that I think should make sense. So that being said, this goes away, that goes to 1, and you can solve for partial z partial x by subtracting this and dividing. So we end up getting negative partial f over partial x divided by this guy in front of this partial z partial x, which is partial f over partial z. Or in short, this is negative f sub x over f sub z. Very similar relation to what we had from the previous result, from the previous screen. Notice the symmetry here, z and x are kind of swapped, but here we have the subscripts which represent partial derivatives with respect to those variables each. And very similarly, if we want these to be y's instead of x's, then now partial x over partial y is 0. Similar reasoning, because x is a variable in the eyes of y. Partial y over partial y would be 1, so that's 0, that's 1. That's going to be a partial z, partial y, imagine. So you're getting a very similar result. You get negative partial, let's see, that would be 1, so subtract that, f over partial y, divided by this coefficient of partial z, partial y in this case, which is partial f, partial z, which I know is a lot to look at, but the end result is definitely believable because of all of the symmetry that's happening here. Perfect. Now for this example, I'm just going to find partial z, partial y, that was a typo, there we go, of this function here, or this expression here. So this is, again, implicit, but it's with partial derivatives now. So we're going to need our capital F of x, y, z function, which notice is just subtracting 1 to the other side. So our capital of x, y, z function must be equal to x cubed plus y cubed plus z cubed plus x, y, z, and then minus 1. Because notice that will indeed give us 0, because just subtracting 1 gives you 0. Awesome. And with that being said, then partial z over partial y in this case, which is what we're looking for, must equal negative f sub y over f sub z. Which is nice to remember again because of the symmetry, it's just swapping these letters, but they represent different things. Now, the derivative of f with respect to y, partial with respect to y, these non-y terms go to 0, that goes to 3y squared. Derivative of this, here the y drops, so we get plus 6xz, negative 1 goes to 0 because that's, that's a constant. And the derivative with respect to z now the x and y terms go to 0, derivative of z cubed is 3z squared. Derivative of this, 6xyz with respect to z, the z drops, so we get plus 6xy, negative 1 goes to 0 because it's a constant. I almost forgot the negative here, so I'll leave that negative in front. And notice here we can divide by 3, very similar to the previous problem. So I'll leave the negative in front though. So divided by 3, we get y squared plus 2xz over z squared plus 2xy. Nice. All right, so that actually completes this discussion on the chain rule. That was quite a bit, and it went a little bit on a tangent to something completely different, but it involved the chain rule. So that was nice and a little epic in some sense. So I really hope you enjoyed this. This actually ends this chapter, believe it or not. And now we're on to new and greater things, and it's going to be a lot of fun. We're looking forward to it. I know you are, and I am as well. So I'll see you in the next videos for that. Hope you enjoyed this. Thanks for watching, and like always, I'll see you then.